Just the continuation of chapter 9, which was about the reactions of alkynes. The last reaction we said it was actually the hydrogenation of alkyne. Whenever we have alkyne, and especially if we have internal alkyne, where here the R is any carbons. For example, if we take specific examples such as, for example, CH2, CH3, and here we have CH3. Then if we allow this to react with hydrogen and presence of Lindlar's catalyst, what we are going to get, hydrogenation of 1 mole, or the use of 1 mole of hydrogen, and converting the alkyne into the corresponding alkene with syn addition reaction. So this is a very important, extremely important reaction. Let me just specify the hydrogens which will be added to this reaction by a different color in here, just to make it more clear. As you can see in here, in this reaction, we have the 2 hydrogens added themselves in a syn addition manner. This is a very important reaction. Do you follow me? While if we allow the same to react with just hydrogens, in presence of palladium, for example, just excess, let's say, excess hydrogen, what we are going to get, just the corresponding alkane, which is in this case 1, 2, 3, 4, 5, the pentane, without any control. Yani we cannot stop the reaction in this direction. We cannot stop it at the alkene. We only can get the corresponding alkane. That's it. But the beauty of the first reaction and the use of the Lindlar's catalyst is that we can stop the reaction at the alkene level, and the alkene here, which we are going to prepare, will be a cis alkene in this case. You follow me? That's actually the reaction what we have discussed in the previous lecture. Now, today we are going to introduce a new reaction. Now, instead of, I'll just keep the Lindlar catalyst. If we allow the same reactant to react now with lithium in presence or in liquid ammonia, what we are going to get, an alkene at the same time, but with different stereochemistry. So we are going to get, now I'm just going to use different color here, hydrogen, hydrogen. As you can see here, we are going to get anti-addition of hydrogen, and then we're going to stop at the alkene. So in here, the use of hydrogen in the presence of Lindlar's catalyst will produce a syn addition, and then we are going to get a cis alkene. And the use of lithium in the presence of ammonia or liquid ammonia, we are going to get anti-addition, where we have a trans alkene in this case. These are extremely important reactions, especially when it comes to the synthesis and converting one functional group into another. Is there any questions so far? Is there any question? All right. So this is, we are not going, the mechanism here, yes please.
This reaction is just for 1 mole?
Yes, it is actually. So this is by default, when we allow this to react with lithium with ammonia, that means we are going to add only 1 mole. We are not going to this reaction will not continue, in other words, to the corresponding alkane. Do you follow me? Is that clear? With these reagents, if we use this reagent with the alkyne, with this internal alkyne, we are going to get we are going to get trans addition. If we get hydrogen with Lindlar's catalyst, we are going to get cis alkene. That's it. In order to get the alkane, we need to react this with hydrogen, with excess hydrogen, and that's it, in presence of, for example, any metal like palladium or or platinum or whatsoever. So we are going to get then the corresponding alkane. Do you follow me? Is that clear now? Is that clear for between the three reactions? All right. But then, as I said, please, if you can, just open up your mic whenever I ask if it is clear or if there is a question, just open up your mic. Now, this is simply, as I said, and this is extremely important when it comes to the synthesis. So we are not going to discuss the mechanism of reaction here. We are not going to discuss it. So you just read it at home, mechanism of reaction, of this reaction. We are not going to discuss it, just you may read it for yourself at home. Now, let's talk about oxidation of alkyne, or reaction with KMNO4 or ozonolysis of alkyne. So, ozonolysis, or let's talk about oxidative cleavage. Oxidative cleavage of alkyne. If we allow this to react with KMNO4 in presence of H+, or ozonolysis, we are going to react it with this, or ozone first, then followed by zinc. What we are going to get, we are going to get oxidative cleavage all the time. We are going to get all the time the carbon here. If we use internal, what we call it, internal alkyne, what we are going to get all the time, we are going to get both sides as carboxylic acid. So we are going to get one side here, which is attached to the ethane, COH. Yes, please. Okay. Clear now? Is it clear now?
Yes.
All right. All right. Now, as you can see here, what we have in this alkyne, when we allow it to react with either KMNO4 in the presence of H+, or ozonolysis, O3 in presence of zinc, what we are going to get, breaking of this bond, and each carbon here, which was carbon attached to another carbon, this becomes COH, carboxylic acid. So then we are going to get this plus CH3 COOH. Do you follow me? This is in case we have internal alkyne, if we allowed internal alkyne to react with oxidative cleavage. What if we have a terminal alkyne like CH3 C triple bond CH? That's actually the difference between alkyne. Alkyne, the triple bond can be within the chain or it can be at the end of the chain. If it is at the end of the chain, we call it always terminal alkyne. Do you follow me? In this case, if we allow it to react with KMNO4 or ozone, what we are going to get, the same. This triple bond will be breaking up. Now this carbon, which was attached to a carbon, this becoming COH. While this carbon, which is attached only to hydrogen, becoming CO2. So what we are going to get in this case, we are going to get for this reaction, we're going to get two products, where one product is CH3 COOH and the other product is CO2 gas. That's it. Yes, please. All right. Again here now, if we have oxidative, if we allowed alkyne to react with KMNO4 or O3. Do you remember this reaction with alkene? The reaction of alkene with KMNO4 or ozone. Do you remember this reaction?
Yes.
What we were classifying this reaction? We were saying this reaction is called oxidative cleavage, right?
Yes.
What's the meaning of oxidative cleavage? It means, in the alkene case, the carbon double bond carbon, it will be breaking up and the two carbons will be oxidized. That's actually the meaning of oxidative cleavage. The same thing here, when we allow alkyne to react with either KMnO4 or ozone. What we are going to get, oxidative cleavage. What does that mean? We are going to get breaking up of the carbon, triple bond carbon. So this bond will be broken. Do you follow me? And each part, the oxidation means each carbon here will be oxidized. How and what's the product? This is what we are discussing now. Now we say alkyne, they can be two types, or they can be classified into two types. They can be internal or terminal. Is that clear so far? Is that clear, guys? Huh?
Yes.
Perfect. Internal means if the carbon-carbon triple bond is just in between carbons. In other words, if the carbon triple bond carbon, this system is connected to another carbon from both sides. This case we call it internal. The terminal, if the carbon triple bond carbon system, they lie at the end of the chain. In other words, we have a hydrogen attached to the carbon triple bond carbon. In this case, we call it terminal. These are the two cases of the alkyne. So whatever the alkyne is, it must be one of the two, either internal or terminal. So this reaction depends on what type of alkyne we are using. If it is internal, it will give us certain products. If it is terminal, it will give us another product. So the product for the first alkyne, which is the internal, as I said, this reaction will proceed via oxidative cleavage. In other words, the carbon triple bond carbon in here will break up, right? Otherwise, and also these carbons, which were making the carbon triple bond carbon, they will be oxidized. Each carbon will be oxidized to the corresponding carboxylic acid. That's it. This is simply the reaction. So what you are going to get here, at the end here, we have CH3 attached to this. This will become COH, and this here will have CH3, CH2 attached to COH. So what we are going to get, we are going to get two carboxylic acid, CO2H, and the other carboxylic acid is CH3 CO2H. Is that clear? Clear now?
Yes, doctor.
Alright, is there any other question, guys? So this is regarding the oxidative cleavage. As you see, it's very straightforward, but just remember what will be the outcome of the reaction. For the terminal, the only differences you can see here, for the terminal, this side, this carbon is similar to this carbon or this carbon. So which means this carbon will become COH when it oxidizes. But this carbon, because it contains hydrogen, so it will be further oxidized. This will always be oxidized to CO2. This is always the case. Whenever you have a terminal alkyne, one of the carbons, which were making the carbon triple bond carbon, will be oxidized fully to the CO2, just gas, and the other carbon will be simply oxidized to the corresponding carboxylic acid. So what we are going to get here, we are going to get CH3, CH2, CO2H plus CO2 gas. What did you notice here? What do you notice regarding the number of the carbons for the terminal alkyne? We started up with how many carbons now? We start the reactant, how many carbons it contains?
4.
The product, how many carbons it contains?
4.
No, the product is 3. because simply the CO2 gas is just gas, will go off, right? So what we are going to get, this product, which is 3 carbons, 1, 2, 3. This carbon here has been like breaking up from the whole system. Do you follow me? So this is one of the reactions where we get like shortening of the long chain here. So from 4 carbons, we are going to end up with 3 carbons. And this is always the case. Whenever you have a terminal alkyne, we are always going to end up with a carboxylic acid with 1 carbon less than the terminal alkyne. Clear? Is that clear, guys?
Yes, doctor.
All right. Let's talk about acidity of terminal alkyne. Again, the terminal alkyne, when we have the carbon triple bond carbon system, is simply at the end of the chain. So let's talk about acidity of terminal alkyne. Now, when we compare the acidity of these hydrogens, C triple bond C hydrogen, I'm just going to specify it in different colors, the hydrogens under investigation. And C whatever here. Oops. Now, if I ask you which of the 3, or arrange these compounds in order of increasing their acidities, arrange the following compounds in order of increasing acidity. Which compound should be the highest acidity? Compound number 1 or compound number 2, or hydrogen number 1, hydrogen number 2, or hydrogen number 3, and why? What do you think? Which compound should be the strongest acid? The first compound, second, or the third, and why?
The first one,
Why?
I think because of the hydration.
Right. So what about it?
SP.
Yes. So what's going to happen? It is SP.
So it is easy to lose the oxygen.
The hydrogen, you mean?
Yes.
The hydrogen. True. That's absolutely true. This carbon here, which is the hydrogen here, attached to sp hybridized carbon. The hydrogen in this case attached to what? sp2. Hydrogen in this case is attached to what? sp3. Right? We know this, and we are not going to rediscuss this. Now, in all of these carbons, what will be the percentage of s orbital in the hybridized orbital? What's the percentage of the s here? In the sp, what will be the percent of the s in the sp? 50%, because simply one s and one p, so it is 50%. 1 out of 2, right? What's the percentage of the s in the sp2 hybridized orbital? Approximately.
33.
Which is the third, 1/3, 33.3, whatever. It's 1/3, because simply we have 1 orbital of s over 3 orbitals, which means 1 over 3 times 100 is 33.3. And the last one will be 25%, right? As you can see here, as the s character increases in the hybridized orbital of the atom attached to the hydrogen increase, simply acidity increase. And this is always true. So as character or percentage, let's say, as percent of the hybridized orbital let's say of the atom attached to, it's not for the hydrogen, because simply the hydrogen never use a hybridized orbital, of the hybridized orbital of the atom attached to the hydrogen, increase, then acidity increase, always. So if the hydrogen attached to an atom which is sp, then the acidity will be higher than sp2, higher than sp3, because simply this carbon here will be more likely to be more positive compared, let's say, compared to this carbon, because simply, as we said, when the hybridized orbital becoming or containing more s character, that means it is closer to the nucleus, which means it is affected by more attractions from the nucleus compared to the other. Clear, guys? Is that clear? As you can see in the table, you can see for the alkyne the pKa is 25. For this is for terminal alkyne, of course, remember. And for alkene it is 44, the pKa, and for alkane it is 60, which is a huge difference in the acidity of the three classes of compounds. But remember, it's all about the terminal alkyne. So here, in order for this hydrogen to be acidic, it must always remember the terminal. This we are talking about terminal alkyne. In terminal alkyne, it has no hydrogen attached to it has no hydrogen attached to a sp carbon hybridized atom. Clear, guys? So it must be a terminal alkyne. You follow me? That's actually this reaction. This is simply, we can use this in the synthesis. Actually, we can use this in application for the synthesis. But before moving, is there any question about the acidity of terminal alkyne? Is there any question?
No, doctor.
Alright, so let's move now for the synthetic application of this idea. So we said terminal alkynes, they have somehow significant acidity, and this acidity we can get benefit out of it. How? Suppose you have, for example, this terminal alkyne, CH3, C triple bond, CH. And when you allow, because this has somehow good acidity, when you allow it to react with some strong base, such as sodamide, NaNH2, what you are going to get, the corresponding CH3, C triple bond, C minus, Na plus, and plus ammonia. So this is actually this is what we are going to get because of this acidity, and this anion called acetylate. This anion always called acetylate. You follow me? Now we must, first of all, about this reaction, we must use this strong base. If we use another base, maybe we are not going to make this conversion. Remember this. So in order to make this reaction take place, we must use the appropriate base with certain power, because we said this is very powerful base. The sodamide here is very powerful base, which has the ability to abstract this hydrogen and to leave a negative behind it. Now this here, this acetyl, it's actually a nucleophile in this case, as you can see here. It is a nucleophile, which means it has the ability to react with, for example, suppose we allow it to react with bromoethane. The bromoethane, as we will see actually in chapter 11, this we will talk about it in more details in chapter 11, but for the time being, you should know that this carbon, which is attached to the halogen, the polarization of this carbon must be partial positive and this is partial negative, which means this nucleophile can react, can attack this carbon, and the halogen will leave. So what we are going to get, CH3, C, triple bond C. Then, as you can see here, we're going to get here the carbons which were attached to the halogen in this case. This is called, this reaction called nucleophilic substitution, SN2. We will talk about this in more details in chapter 11, and especially in chapter 11 we will simply explain the mechanism of this reaction in very much details. But for the time being, all what you are required to know that this nucleophile can attack any primary alkyl halide, all right, and this halide, this acetylate, it will simply displace the halogen and we are going to get this alkyne. In other words, we can convert terminal alkyne into internal alkyne, as you can see, by adding carbons here. Clear? Come again, please. Would you please repeat your question?
I mean, the structure above, it's not terminal, it's internal.
The previous structure is terminal, right? The reactant is terminal and the product is internal, right? This is internal alkyne here. This is internal and this is here terminal. Is this your question?
Yes.
Okay, so what's the difference between is your question about terminal and internal? This is terminal because simply one of the carbons attached to the hydrogen. In this case here we call it always. Whenever we have a hydrogen attached to a carbon triple bond carbon, we call it terminal. If there is no hydrogens, if there is just carbons, we call it internal. Do you follow me? All right.
Yes.
So anyway, did you get the reaction, guys? In general, the reaction is simply here like two-step reaction. First, reacting terminal with sodamide to produce the corresponding conjugate base, اللي هو acetylate. This conjugate base, اللي هو acetylate, can react with, you can see here, with any primary aldehyde, with any primary alkyl halide. Do you follow me? Cannot react with anything. It's just must be primary alkyl halide. You see, halide, when the halogen attached to the carbon, it can be classified into primary or secondary or tertiary, right? For example here, CH3, CH3, CH, CH3, Br, CH3, C, CH3, CH3, Br. Here we call this primary alkyl halide. We call this secondary alkyl halide. We call this tertiary alkyl halide. What we mean by this reaction is only this reaction. Whenever we have primary alkyl halide. Primary alkyl halide means the halogen attached to what? To a carbon which is primary in this case. This is here, the classification of this carbon, you can see, it's primary because it's only connected to one carbon. You got it? So it's extremely important to remember that the only alkyl halide works in this reaction is primary alkyl halide, not any halide. Yani the secondary does not work, as we will see in the next slide. The tertiary does not work. Only primary alkyl halide can react by this way. Got it, guys? Is that clear? Any question?
No, Doctor.
All right. Now, let me just give you, now this here, I just want you to focus what has happened. You can see we have changed this compound. How many carbons we have in the reactant in this reaction? How many carbons?
3.
How many carbons we ended up here?
4.
5, there's 4.
5.
5, right? Isn't it? It's to be converted 3 to 5. This type of reaction we call it long chain or elongation of the long chain. This is elongation. You can say this is elongation of the chain. Do you follow me? Like we can increase number of carbons by this reaction. In the previous reaction, if you remember, when we had a terminal alkyne, we allowed to react with carbon-4 or ozone, we have like shortening up the chain. Yani we reduce the number of the carbons. Here, we are increasing the number of the carbons by this reaction. Just to make the story short, you must remember this. This reaction applies only to terminal alkyne. We must have a terminal alkyne for this reaction to take place. If we don't have terminal, then the whole reaction will never work. Why? Because we need a hydrogen here to be acidic, which is the terminal alkyne can provide us with this. Is that clear, guys?
Yes.
So this is very important thing. First thing, we remove this hydrogen. We convert the terminal alkyne into its corresponding conjugate base. Once we have the corresponding conjugate base, we allow that base to react with primary alkyl halide. Again, must be a primary alkyl halide. Any other halide does not work. Must be primary alkyl halide. I think you should all know by this level that this halide is called primary because simply the carbon attached to the halogen is a primary. Therefore, the whole alkyl halide is a primary. So that's the second requirement needed to make this reaction happen. Otherwise, the reaction will never work again. So if we allow the acetylate to react with primary alkyl halide, what we are going to get some sort of substitution reaction, nucleophilic substitution reaction, where the nucleophile will substitute the halogen, and then we are going to get elongation of the chain. As I said, regarding the mechanism, we are going to explain it in very much details in the coming chapter, which is chapter 11. And this type of reaction, we call it nucleophilic substitution reaction via SN2. Now, this here will produce or will lead us to a very important aspect in the organic chemistry, which we call it organic synthesis. And the organic synthesis is a very important topic in our life because simply organic synthesis. The organic synthesis, as I said, it's a very important topic in our life because we need to design and we need to synthesize and we need to prepare certain compounds which fulfill certain conditions in our life. For example, like drugs, like industrial application whatsoever. So we can, by the organic synthesis, we can design, we can simply think how to convert one starting material into different product. So let me just give you an example of this. Just as an example, how can you convert the following reaction? How can you do the following conversion? Starting from let's say ethane how can you synthesize let's say cis octane and another example, for example, cis octane. Okay, that's it. This is simply a very common question, and you must practice and you must simply learn from now on how to get familiar with this type of questions, because typically organic knowledge is some few aspects in every functional groups. We should be able to know the nomenclature of a certain functional group. You should be able to know some aspects about the physical properties of the functional group. You should be able to know reactions of this functional group, converting this functional group into another. And finally, you must know the synthetic methods. How can we synthesize, or what we can do with this functional group, or how can we prepare this functional group from other functional groups. So again the best thing always as organic chemists to convert the words into chemical reaction. So we need to start from ethane. This is simply the ethane, CH3, CH3. We need to convert this into cis octane. The cis octane is simply C+C, CH2, CH2, CH3, and then CH2, 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 CH3, and then hydrogen, and then hydrogen. You got it? You get to the question?
Doctor?
Yes, please.
In the questions you write octane, but you draw something else.
Oh yes, I draw decay. It doesn't matter, just make it cis decay. Alright? Decay. You can say anything, but just the idea. What's important is here simply the idea. Got it? Fine now? Is this clear now?
Doctor, I mean you draw something with double bonds. But we...
Yeah, you are right. Sorry, how many carbons is this here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it is, you are absolutely right. Thank you so much. Okay, so it says decene. This is here what I want. Is that clear now? Is that good?
Yes.
Thank you so much. I really appreciate it. All right. Now, actually, for the organic synthesis, whenever you deal with this type of question, you need to follow a methodology which we call it retrosynthesis. Retrosynthesis. What's the meaning of retro? Retro is like, we are going to go backward. We're going to analyze the synthesis starting from the product, going slowly, stepwise backward until we reach up the starting material. Because you can imagine, in principle, we could synthesize, we could do this conversion in one step. We could do it in 2 steps. We could do it in 10 steps, in 15 steps. Do you follow me? So sometimes it's becoming difficult to follow up all these steps. The best way to do it, or to do the whole synthesis, by this methodology which we call it retrosynthesis. what's the meaning of retrosynthesis? We start up with a product. Here, the product is, what's the product? Analyze the product. What do you have it here? What we classify the product? It is what? The product is what? The product is what, guys? What type? What's the class of the product? It is alkene, right?
Yes.
And what's the stereochemistry of the product? It is what? Cis. Isn't it?
Doctor, but in the left carbon, it is below, but the second carbon, it's above. So it will be trans.
Yeah, you are right. Wallahi. I'm just writing something and then simply meaning something else. True, you are right. Thank you so much. This is true. This is here. It must be a hydrogen, and that will be the cis. Okay, thank you. But anyway, we will come to the trans. That's not a problem. Again, is here simply the product, the idea. What's important. Now, what we have a product. The product is what? Cis alkene, right? Now, what method we did study to get as a product cis alkene? We did it today. What reaction we did study in which we get specifically cis alkene? You forgot, guys? What was the reaction?
The last reaction.
I'm sorry?
The last reaction, because the number of carbons is increased.
No, forget that. I'm just asking you here. What a reaction can give you specifically cis alkene? We did as a product, cis alkene as a product. Not trans, not anything else, just cis alkene. Hajar, hydrogenation of what, Hajar? It's hydrogenation, but of what?
Of alkyne.
Of alkyne, exactly. So in this case, what does that mean? This is actually the thinking. This is what we call it the retrosynthesis. That means we can get this from the corresponding alkyne. So if this is C triple bond C attached to CH2, 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 CH3, CH2, 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 CH3, what was the reagent capable of converting this alkyne into cis alkene? It was, if you remember at the beginning of the lecture, hydrogen in the presence of Lindlar's catalyst. Isn't it? This was the reaction which we already studied at the beginning of the lecture, isn't it?
Yeah.
All right. So we got this. So now we have alkyne. Now, as you can see here, we can think of this is alkyne. Okay, let me just for in order not to make it too much long. This is a little bit complicated question. Let me start from ethyne, not ethene. Ethyne first. Ethyne. You follow me? So I'm just going to change this into ethyne. I will come back to the ethane later on. Now here you can see now this reaction, you can imagine it's a terminal alkyne, isn't it? It's like these two carbons are here. How can we introduce an alkyl group here? And how can we introduce alkyl group here? We know this because we just said terminal alkyne can be elongated to a longer chain by a series of two steps. First step by reaction with sodamide, and then second by reaction with alkyl halide. The same thing is the same. In this case here, that means one of these alkyl groups can be introduced. This is simply from the corresponding CH, C triple bond C, then CH2. I'm just going to repeat it this way. So this CH, C triple bond C, then CH2, 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 CH3. Do you follow me? We can introduce this alkyl group by two-step synthesis. By first reaction with sodamide, second by reaction with this alkyl groups. How many carbons here we have? We have to introduce. How many carbons? 1, 2, 3, 4. So 4 carbons attached at the end to the halogen. So see here what? CH2Br, then CH2, CH2, CH3. This is the first step. In here, if we have this terminal alkyne, we allow it to react with this primary alkyl halide. We are going to introduce the product. Now, we just start the reaction from here. So it's a C triple bond CH. This is simply the question. Is that clear so far, guys? Is that clear how we introduce the first alkyl chain? Is there any question? Is there any question? Hello? All right. Now, similarly, now we can simply introduce this alkyl group from the corresponding alkyne. So this is simply can be prepared from this alkyne by two-step synthesis. First with sodamide, second with the primary alkyl halide, which is in this case CH2Br, CH2, CH2, CH3. Do you see it? This is how we could achieve the synthetic procedure, the synthetic protocol. So starting from ethyne, we could simply prepare the cis decane by simply these steps or this sequence of steps. How many steps we need? This is all is one step. This is second step, and this is third step. So we can do it by 3 steps. We can convert alkyne into the corresponding alkane in this case. Clear so far? Is there any question?
No, doctor.
Is it clear so far? Okay, good. Everything is clear. Is everything clear? All right. Let me just give you more questions about the synthesis, because actually this is the end of the chapter, but let me just give you more examples about the synthesis. Yani, remember, just to make the story short, whenever you have R, C triple bond C, H, terminal alkyne, remember always that you can simply introduce another R here by 2 steps. By first, sodamide, by taking off this hydrogen. Second, by reacting with primary, let's say, R prime alkyl halide, for example. In this case, you can produce another, or we can introduce another R prime here. And then you can convert this, for example, into trans alkene. Or you can convert it into cis alkene. Or you can oxidize it, for example. You can take this carbon off for any reason. You can simply convert it into R, these 2 carbons off. You can convert these 2 carbons off by R, CO2H by simply KMNO4, for example. Here, by simply reacting with ammonia with lithium. Here, by reacting with hydrogen in presence of Lindlar's catalyst. Do you follow me? So we have plenty of options actually for this reaction. So it is very important synthetic procedure for actually this step, or this two-step synthesis is very important in the synthesis. We can get a lot of benefits out of this reaction. I was actually thinking to start a new chapter, which is chapter 10, but I think it's better actually we start the whole chapter at once in one chapter, because we need to finalize it. Anyway, I decided not to give you any lecture for this afternoon. What I'm going to do in this afternoon, I'm going to upload a homework assignment for alkene and alkyne, alkenes and alkynes, and this homework you're supposed to, or this assignment you're supposed to submit it next week, in order for you just to keep up with what we are studying and not to, not to keep a lot of material which is not studied in the appropriate time. Clear, guys? So you will have assignment. We are not going to take another lecture today. We are just going to, there is no lab. There is no lab for this week because due to the holiday this Wednesday, Ahmed, there will be no lab today, this week. There will be only assignment. So I want you to, to get trained, to get practice, and not to forget what we are studying. So we are studying the chapters fast. So therefore, I want you to keep up, not to lose the information what we are studying. Clear? So, yes, please.
It is enough assignments for us. We will study.
Wallahi, you are making me confused. If I don't give you assignment, you will complain that you are not studying, you are not understanding well, and you need more assignment to understand, and so on and so forth. If I give you assignment, then I am bombarding you with a lot of work, and so on and so forth. So what's the best here? What do you think? It's for me. Remember, for me, it is more work. Assignment, to give you assignment, and then simply to mark everything, and all of your numbers will be a lot of work to me. But I'm doing this for you, to keep understanding and to find your weakness, because sometimes you don't want to go to the exam and then simply, shaken with a new type of questions which you have never ever thought about it. Do you follow me?
Yes, doctor.
That's actually the case. So, to be honest, actually, I'm doing this for you. That's the whole issue. Taslim Isbu al-Qadim. Regarding the assignment, I'm going to give it to you. I'm giving you enough time. So today is Monday. It's fine. You can submit it until the next Monday. You will have enough time to do it. Clear, guys?
دكتور حتى لو Wednesday.
Wednesday will be the exam. The one who was asking. Right?
زين حتى ولو يكون نذاكر ونحل يعني يناسب.
Okay, fine. It's fine. Okay, let's make it Tuesday evening, in order for you to be sure that you are doing it perfectly. It's fine. So you will find the details actually in the Moodle. Layl, what are you saying? I don't understand. What are you writing? طيب, because you are studying by all means to the exam next week, isn't it? So while studying, you can be easily, if you cannot solve assignment while you are studying for the exam, there is a problem. You must be, the assignment should be a piece of cake to you, because you are under free of pressure, whatever. You are just doing it like you're understanding something, and then simply you are answering it. which مصايب? Which مصايب أحمد? There is no مصايب يعني. There is just science, and you are studying science where we should enjoy science, not studying, not يعني we shouldn't crying for science. We should enjoy our life with the science. Okay, and now for Yahya, for the exam, the second exam, it will be fully multiple choice question this time. I want to check this methodology. So it will be fully multiple choice question.
دكتور
Yes.
بس لو سمحت حدد لنا شباتر بالاسم، ما تعطينا 5 6 7 8 لأنه المرة الماضية كذا وفي الأخير في دخلتنا يعني مال الكيز وما دخلت الرياكشن.
طيب. Okay. Alright. Today in the Moodle, I will simply assign for you the assignment. I will upload the assignment, and as well I will mention specifically each chapter with the title, with the sections which will be included in the second exam. It's fine?
أيوة شكرا.
إن شاء الله ولا يهمك. بالنسبة للفاينل طيب. بالنسبة للفاينل الفاينل as I said in my WhatsApp, once the university approve, our final exam will be held at the SQU University. It will be في الجامعة. The final will be held at the university if the administration approve for that. So until now, we're waiting for their approval. If they approve, then we'll do it in the university. If not, then that actually will be online. Okay? Clear?
دكتور بس نريد يعني شيء اكيد احنا بوقت.
Okay, I will ask that HOD today just if I can confirm to you that it will be at the SQU or not. So today, maybe by this week, inshallah, or maximum, by the end of this week, you will hear from me confirmation perfect that the final exam will be at SQU or final exam will be online. Because as I said, I cannot confirm without the confirmation coming from the administration of the SQU, because that's actually not my only decision. It's a decision of the university. If they approve it, if they confirm it, I will confirm it to you. Is that fine? Alright. Okay, شكرا كثير لكم. Wish you a very good day and a very joyful vacation for the next Wednesday. وكل عام وانتم بألف خير إن شاء الله، وربنا يعيده عليكم وعلى عمان وعلى الأمة العربية الإسلامية كلها بالخير واليمن والبركات. أشوفكم على خير إن شاء الله.